The IARPIC Modeling Collaborative Team focuses generally on the representation of the Arctic climate and processes in Earth system models and reanalyses and in regional climate models. We welcome participation from model developers, those who use and evaluate models, and those with an interest in the Arctic climate. So welcome everyone. There's been a lot of discussion in the research community on atmospheric rivers. I was at the AMS meeting in Madison last week, and there was certainly a lot of discussion of atmospheric rivers there and their role in the climate system. So disagreements in detection methods led to ARTMIP, the Atmospheric River Tracking Method Intercomparison project, which culminated this year. Significant differences in available tracking methods were found in ARTMIP, which may be related to how atmospheric rivers are defined. The Arctic and polar regions in general are thought to be particularly susceptible to the episodic nature of atmospheric rivers and their associated precipitation and warm air intrusions. Thus far, though, there has been not very much work published in assessing Arctic atmospheric rivers and climate models. So to help us with these issues are two researchers associated with atmospheric river studies and with climate models. So we'll begin with Christine Shields. She is a project scientist with the Climate and Global Dynamics Laboratory at the National Center for Atmospheric Research in Boulder, Colorado. And she will talk on what is an Arctic atmospheric river. Christine?
Okay, I will share my screen. And you guys can tell me if there's something wrong. Otherwise, I'll assume everything's sort of okay.
That's good. It's good.
Okay. All right, I'm gonna actually move this box so I can actually see my slides and shut down the chat. So I'm not looking at the chat right now. Okay, well, thank you for the invitation. I really appreciate being able to speak to you today. I also would like to acknowledge my collaborators, Rudra and Steve at University of Wisconsin, Alice, Laura, and Marika are sitting with me here at NCAR, and of course the whole ARTMIP community, which is the Atmospheric River Tracking Method Intercomparison Project, which Richard actually already really nicely introduced. So I am a part of the Catalyst team, which is actually funded by DOE and the Office of Science. And the rest of the team is funded under various NSF projects. So thanks to all the funding agencies. Oops. Okay. So before I actually start to talk about what an Arctic atmospheric river is, I thought I would just sort of back up and just so we're all on the same page on what a regular or whatever regular means, atmospheric river. So I think perhaps just looking at everyone that's on the call, that probably most people understand what an atmospheric river is, but I just will give some basics here just so we're all on the same page. Atmospheric rivers tend to be these long filamentary synoptic scale features that transport moisture across climate zones. I have this nice little GIF which shows a classic atmospheric river making landfall or going across the Pacific and making landfall at West North America. These things tend to have a variety of types of impacts. They can be very beneficial and help relieve drought, or they can also be very destructive with lots of floods and extreme precipitation. So the question here for us is, what's the difference between a regular atmospheric river and an Arctic atmospheric river? And the way I tend to view it is that the Arctic atmospheric rivers are essentially these same sort of synoptic scale features, but they penetrate into the Arctic. And this video I sort of grabbed from the NOAA website. It shows a series of atmospheric rivers making landfall in and around Greenland. This was at 2016 in July, back in 2016, number of years ago. So you can see, and this is precipitable water that we're looking at. So the types of impacts that an Arctic atmospheric river would produce would be you probably would also need to add into that like severe or significant accumulation over glaciers, for example, over Greenland. Or on the flip side, warm air intrusions or heating events that would cause melt on the glacier. So these are types of things I think we're interested in when we're talking about Arctic atmospheric rivers. So I took 2 snapshots from the SSMI satellite imagery. This is precipitable water that we're looking at here for 2 different examples of Arctic atmospheric rivers. So this one was just last year, August 14th, where there was this really broad atmospheric river that made a pretty big impact over Greenland. It was the subject of a case study by Jason Box that was published in GRL earlier this year, where there was a really significant melt event on the Greenland ice sheet. This study by Box et al. Actually found that it wasn't necessarily the rain on snow that was the impact. It was actually more the radiative impacts, the latent and insensible heat and the long wave radiation that actually contributed to that melt, more so than the rain. So that's a very interesting study. The other example is this one that I found that stretched actually all the way to Nome, Alaska. Typically, you have a very common atmospheric rivers will make landfall on the southeast coast of Alaska here and in the upper Western North America. And this is sort of right on the storm track, and you often see these track right into the West Coast, but it's less often that you actually see them reach into places like Nome. And in this particular atmospheric river was actually a record event where I think the 24-hour rainfall record was broken. So that was also a very significant atmospheric river event that we would care about. So so these are just sort of snapshots and examples of atmospheric rivers that I've given you, but what we really want to do in this group, we care about climate models. So we use climate models to predict and project AR behavior and trends, but how do we represent these ARs in gridded data sets? We're not looking at snapshots of satellites. We have things like MERA or ERA5 reanalysis. We have climate model data, and this is all gridded. So how do we actually define and detect atmospheric rivers in these types of data sets? So this is sort of where these things called atmospheric river detection tools come into play. And there's many different types of ARDTs. That's the acronym ARDT for Atmospheric River Detection Tool. And the little GIF I have that's cycling through here is the variable that we're looking at is integrated vapor transport, but the red outlines are just one example of an automated ARDT that's defining an atmospheric river in that footprint for purposes of analysis in our global model data. So because a lot of these different ARDTs have fundamentally different science questions that they're answering, or they actually define an atmospheric river differently, they're very different between the different types of detectors. So this is where ArtMIP sort of comes into play, where the goal of ArtMIP has always been to understand and quantify uncertainties in our science for atmospheric rivers, just solely based on how we're detecting and defining them. And so one of the things that ArtMIP does is it designs experiments where we have a baseline data set that, and all the participating ARDTs that are part of ArtMIP will run their algorithms on this same data set, and then we can compare apples to apples, and then actually compare the difference between the different ARDTs. So this figure is sort of similar, sort of what I'm talking about. So I'll just sort of draw your attention here to the left a little bit, where we're looking at, I took 2 snapshots. I know we're focused on the Arctic here, but I've also done some studies with the Antarctic, and it's high latitude, and a lot of these concepts apply to both, northern hemisphere and southern hemisphere. But so here we have the base of the plot are these shades of blue. This is the integrated vapor transport, the IVT value. And this is the deeper blues are the stronger values of IVT. And these individual little different color contours are the spatial footprint outline of all the different ARDTs, all the different ways of detecting atmospheric rivers. So you can see for this atmospheric river that's stretching into the Labrador Sea next to Greenland, you have most of them will agree that there's an atmospheric river there, but what the spatial footprint is widely different between each of them. Some of them are just the most intense bit of IVT is being detected, and other ones you have a broad spatial footprint. And then over here by the Hudson Bay and Great Lakes, you have some detectors that are actually capturing what is likely an extratropical cyclone. So then, you have all this, is it a false positive? Is it not? All these different things that you have to consider when you're automating and detecting these types of features. So broadly, what I'd like to do, at least for the purposes of this talk, is to sort of divide these up into like global ARDTs and regional ARDTs. And the global ones, they're designed to detect atmospheric rivers across the whole globe. And so they focus on integrated vapor transport, but they also use the full, the vector quantities. So U and V, both components, zonal and meridional, of IVT. And here's the equation. It's just the moisture and the wind integrated throughout the atmosphere. Another way of detecting or using a moisture threshold in these ARDTs is integrated water vapor, which is simply the moisture integrated throughout the atmosphere. But most of the globals do have this zonal and meridional equal weighted in terms of what they care about for moisture and for geometry, for example. Where the regional ones that are available that are participating in ArtMIP, both of them are developed by Jonathan Willey. He focuses on meridional geometry. And so, for example, one of them just looks at the V component of the integrated vapor transport. And the purpose of this one is because he really just cares about the integrated vapor transport that's penetrating into the deep parts of the Arctic. So this is just to sort of, queue up potential discussion later. Is like, what is an atmospheric river, and what's the difference between an atmospheric river and an extratropical cyclone? And I could probably throw in there moisture intrusions too, because people often exchange atmospheric river and warm air or moist air intrusions as well. So my view on these types of things is, and there's lots of different types of views, is that atmospheric rivers, to me, imply a transport of moisture across climate zones. ARs can be extratropical cyclones, but not all extratropical cyclones are atmospheric rivers. And that could be something like moisture intrusions, or ARs could be a subset of a moisture intrusion, where moisture intrusion may not have a geometry, that is typically defined with it, but an atmospheric river does. So those are just types of things for us to think about and potentially discuss. So just to dive a little bit deeper into, the ArtMIP algorithms that are out there, I sort of took out 3 representative ones. And this is work I've been doing with Rudra at University of Wisconsin. So these plots are his. So I want to make sure, proper attribution is given to all the different plots. So there's 3 ones I'm looking at here. Bin Guan and Dwayne Wallace are developed an algorithm that's a global. It's very commonly used across the whole community. It does have logic in that ARDT to account for polar atmospheric rivers. So I call that global and polar constraints. And it basically is this relative method that computes the 85th percentile in terms of moisture thresholds. And so that's this one right here. And it doesn't necessarily get to penetrate deep into the Arctic or over the ice sheets, but it does do a really good job of detecting atmospheric rivers in the North Atlantic storm track, for example. The Mundak algorithm developed by Brian Mundak when he was a grad student at CSU is this one right here. It's a stricter thresholding requirement. It doesn't get anything in the Arctic, for example. It just really is just sort of mid-latitude focused, even though it's computed globally. So this one may not be appropriate for Arctic studies, for example. And then Jonathan Willey's ones, where this one is a high latitude specific one. It's regional. It's very strict in terms of what it requires as an atmospheric river. It's just picking out the strongest storms, and it picks out the hot spots around the Arctic where you have these meridional atmospheric rivers that are making it into the interior. You can see the Willey one does really the best job at capturing ARs on the ice sheets, for example. Okay, so this is just sort of another way of looking at it. These are what I call heat maps. It's just an accumulated and just adding up all the atmospheric rivers that all the different algorithms do. And then I'm subtracting out the global from the regional. And I'm showing you both the Arctic and the Antarctic here. The warm colors are essentially where the regional ones, these meridional focused ones, do a better job at capturing the interior. And then, so the cooler colors are where the global ones are capturing more for atmospheric rivers or extratropical cyclones that are also associated with atmospheric rivers. So you can see the globals clearly do a better job in the North Atlantic, but the regional ones do a better job over these high dry regions. And this concept is the same for Antarctica, where the interior of the Antarctic, especially in Eastern Antarctica, really needs that meridional piece to it. All right,
Christine, this is your 2 minute.
my 2 minute. Okay, that's great. So that's good. So this is just sort of a different way of looking at what I just sort of showed you, but just from all the different, we've got like 25 different algorithms here that you can see all the different, values that they're detected, and then I've sort of normalized it here by type, where the IVT 100 is the polar threshold one, and you can just sort of the idea where the polar detects more compared to the regional. One other thing to realize about the ones that, if you have a really strict requirement and they're only getting the ones that penetrate deep into the Arctic, that really only happens a few times a year. So those, instead of like happening 12% of the period, it might only happen 1 to 2% of the time. I'm going to skip this because Weiming is actually talking about sea ice. And so this is work that Rudra is doing, but I'm going to just skip this and let Weiming talk about the sea ice and atmospheric rivers in his presentation next up. The remaining thing I wanted to actually communicate was how we look at these in large ensembles, because we are talking about, this is a modeling group, so I did want to touch on models. And so here we're looking at the CSM2 model, and we're looking at the large ensemble. And the takeaway from this is that you need to sort of be careful how you use your detectors when you're looking at large ensembles. You actually want to compute your detectors and tracks on each ensemble member, and then do a greater average of that, rather than just run the detector on the ensemble mean, because the ensemble mean will not necessarily reflect the interannual variability. So, but when you do it the proper way, with just looking at, this is just using 10 ensembles, but we've done with all 40 ensembles and it looks the same. The CSM2 actually does a pretty good job at representing the different hotspots around the Arctic. And here we're using the Arctic specific ones. So we're really looking at the hotspot regions in these high dry locations, and cooler, higher and drier locations. And this is simply the standard deviation compared to the mean using the CSM2 large ensemble. And the standard deviation hotspots essentially mimic the hotspots you see in terms of where the frequency is. And this sort of makes sense. Where you have the most ARs, you actually have the most variability. All right, so to summarize everything for takeaway points, atmospheric rivers indeed reach into the Arctic. They bring large amounts of moisture and precipitation, typically coming from the mid-latitudes, and they can have severe impacts. There are many ways to define and detect atmospheric rivers in the literature. So my advice would be to choose wisely and choose your ARDT that it matches the science question that you're asking, because there's many choices out there, and not all of the detectors are appropriate necessarily for the science questions that you're interested in. Generally, this is generally global ARDTs do a better job in the storm track, and the regional ones will are more appropriate for interior locations such as ice sheets or storms that are more meridional focused, that actually penetrate deeply into the Arctic. And then finally, in terms of the modeling stuff that we've done so far, the CSM2 historical models actually agree quite well with our hotspots around the Arctic compared to the reanalysis. And we are looking forward to our future work, looking into the future using the CSM2 SSPs, and then folding in the E3SM model as well. So I will stop there and then throw it over to Weiming, and then we'll discuss, I think, after both presentations. Okay.
Thanks very much, Christine. I think we do have time for a few clarifying questions. I had one just going back to the idea of modeling. The idea, one of the aspects of the definition of an atmospheric river is that it's a thin filament. So model resolution, I would imagine, plays a significant role in in the representation in models. Could you just comment on that to some degree?
Yeah, no, resolution actually does make a big difference, especially when you're quantifying the impacts, such as precipitation. In my my research, I find that the high resolution models do a much better job at capturing the impacts of atmospheric rivers than, say, like the standard resolution. But there's trade-offs, right? So like, well, high resolution, you can't do ensembles necessarily much, you know, because it's really so computationally expensive. So that's, yeah, so, you know, it really depends on what you want to look at. But yes, I do agree, the resolution does matter. We have, the ArtMIP actually has a paper out comparing ERA 5 and MERA 2, which or MERA 2 is about a half degree and ERA 5 is quarter degree. And there are, I mean, in addition to like just the model differences, you do see a resolution signature in there. So it's just a different, you know, the resolution will just, you know, even for like the ARs that have geometry requirements, often they'll have to be retuned depending on what your resolution is, because you're, you know, what you're defining as your length may differ depending on what your resolution is, for example.
I appreciate you're using MERA too. Mike McCracken, would you like to unmute and ask your question?
Okay, thank you. It was very interesting. So looking at the graphics you were showing, most of the filaments are sort of almost always over the ocean. They really don't extend over land. Does that imply that I mean, and then I guess they run into orographic features and that just drains them out. So that means most of the water vapor is nice and low in the atmosphere. And is that what creates the strong radiative influence on the surface, having so much water vapor down low?
Yeah, you know, I had like an extra slide where I showed the meteorology of vertical structure, but I didn't have time. So it's actually, if you download the talk on the PDF, you'll see it in the extra slides. But if you go to the Bulletin of Atmospheric, or the Glossary of Atmosphere, the AMS Glossary of Meteorology, there's a nice schematic that shows you that vertical structure. But yeah, because the moisture, it's mostly more the atmospheric rivers are often associated with the low level dret, and so this warm moist air is definitely more in the boundary layer. So, you know, 700 millibars and below is where you're going to have your biggest impact. Atmospheric rivers can penetrate into the interior. You do have examples of like atmospheric rivers making impacts in the continental divide in the, you know, in the US, for example. There's a couple of case studies that are out there that will describe those types of storms. But generally, the moisture is lifted. I mean, the moisture is lifted and then it condenses and then, you know, forms precipitation and all rains out. So you see like some places like in the Western US, the Sierra Nevada depends on a lot of ARs for their snowpack, for example. So yeah, you can get ARs, you know, penetrating into the interior, but they definitely do precipitate out. Yeah.
And Ruping Mo, would you like to unmute and ask your question?
Okay, yeah, it's very nice talk, Christy. It's not a question, kind of a comment. I think for atmospheric river, we usually think about heavy precipitation and strong wind. For Arctic area, as you mentioned, the other issue could be also important. We have this heat transport also associated with atmospheric river. In Arctic areas, we don't have too many people, so the weather, like heavy precipitation, strong wind, may not have that kind of impact as we have in lower latitude here. But for heat transport, that could be very important for climate, global climate. So what do you comment about this, the importance of heat transport?
Yeah, that's an excellent point. I had looked a little bit at the sensible and latent heat transport via atmospheric river, although I did not look at it penetrating into the Arctic. But I think that actually there are a number of studies that actually do that. I'm actually thinking of Deanna Nash as using the Gwan-Walliser method. I might have something. I might be misremembering that, but it is definitely an important consideration, especially that example I gave in terms of the Greenland atmospheric river that happened last year in August, where you had had a melt event at the top of the Greenland ice sheet, and that was there was that paper that did that case study that said essentially what caused the melt was the radiative effects, not necessarily the rain on snow. So the transport of the heat, the water, and the energy are both equally important. I completely agree with that.
Hailong, do you have a quick question?
Yeah, I do have a quick one. Thank you, Christine. My quick question is about the Jonathan Whaley. So that method seems like have pretty big, give big discontinuity in the AR frequency between the Arctic and the lower latitude, especially over the Atlantic sector. What is the main reason for that?
So Jonathan's, that algorithm is a meridional focus one. So it's only really looking for the 98th percentile of the meridional component of IVT, and a lot of those North Atlantic ones are zonal. And so, or the zonal is, there's zonal and meridional, but the zonal is the dominant wind direction. And so it's probably, I think that algorithm is not picking up those zonal ones, just, you know, that sort of are along the storm track. These are where the globals do a much better job.
I see, that's interesting. Thank you.
Yeah.
All right, let's go to our next presentation then. Our speaker will be Weiming Ma. He is a graduate student with the Department of Atmospheric and Oceanic Sciences at the University of California, Los Angeles. And he will present on atmospheric river response to Arctic sea ice loss in the Polar Amplification Model Intercomparison Project.
Okay,
Weiming, thanks for joining us.
Yeah, thank you for the introductions. Let me just share my screen. So okay,
And we can
thank you
see your
for-
presentation.
Okay, cool. Yeah, thank you for this opportunity to present my work. So in this talk, I'm going to talk about atmospheric river response to Arctic sea ice loss in the Polar Amplification Model Intercomparison Project. So this work was done in collaboration with my advisor, Gang Chen, and Yan Lippens from UCLA and a former undergraduate researcher in our group, Noah Avi. So what is the atmospheric rivers? So atmospheric rivers are long, narrow, and transient corridors of storm moisture transfer in the atmosphere. So earlier study found that ARs are responsible for more than 90% of the polar moisture transfer in the atmosphere. And later on, people also realized that ARs are not only important water suppliers to many coastal regions, and they are also behind many of the extreme weather events. And then in recent years, it's also increasingly recognized that AR also play an important role in the polar climate, as just discussed in Christine's talk. So for example, AR can induce a strong sea ice loss and ice sheet melting. But we believe the interactions between ARs and Arctic sea ice is not a one-way interaction. It's a two-way interaction. While ARs can induce Arctic sea ice loss, the Arctic sea ice loss itself can influence ARs. So the goal of our study is to understand how Arctic sea ice loss can influence atmospheric rivers. So here's the outline of my talks. I just give a very brief introductions, and I'm going to next describe the data and the methods used in our study. And this will be followed by the AR response to Arctic sea ice loss. And it's also known that models tend to suffer a small signal to noise ratio when response to Arctic sea ice loss. So I will also try to understand the uncertainties by decomposing this uncertainty into a dynamic and a thermodynamic component. And I will also try to look at the uncertainty from the perspective of internal variabilities versus model difference. Lastly, I will explore potential emergent constraints which may help to reduce the uncertainty in response to Arctic sea ice loss. So in these studies, we use 9 models, and each of these models with 100 members from the Polar Amplification Model Intercomparison Project. And these are atmosphere-only type-site experiments. Each member only consists of 1-year simulations. 2 experiments are used. The first one is driven by present daisy super temperatures and pre-industrial Arctic sea ice concentration. And the second experiment is driven by present daisy super temperatures and future Arctic sea ice concentration under 2-degree warming. And we will focus on the winter seasons, as this is the active AR seasons in the in the northern hemisphere, and also previous study have found that AI response to RTCI loss or atmosphere response to RTCI loss tend to show a strong signal in this BJF season. The AI response will be decomposed into a dynamic component and a thermodynamic component in these studies. And to get the dynamic components, the moisture field in the future RTCI experiments is scaled by scaling factors, the QPI divided by Q field, and here the QPI and the Q field is just winter mean specific humidity for the pre-industrial RTCI experiment and future RTCI experiment respectively. So by applying this scaling factor to the moisture field in the future RTCI experiments, we scale its moisture field back to the pre-industrial RTCI experiments, so that any change in the AI specificity in this case can be simply caused by the change in the circulating field. And to obtain the thermodynamic contributions, the moisture field in this case, the moisture field in the pre-industrial RTCI experiment is scaled into the futures by scaling factor Q field divided by QPI. So that in this case, any change in the AI statistic can be attributed to the change in the thermodynamic field. So now let's first look at the total response. So in panel A, the static contour are showing the response and the solid contour are showing the climatology. So in this study, we will only focus on the response of the AI frequency, and the frequency is just defined as the fraction of time required experience AI conditions. So as you can see that the largest response tend to occur over the ocean basins and over the North Atlantic. In response to RTCI loss, AR frequency increase over the equatorial sides of the climatological AR maximum regions and decrease over the polar sides, indicating the equatorial shape of AR. But however, if we look at the North Pacific in response to RTCI loss, the AR is stand northeastwards. We then decompose this total response into a dynamic component and a thermodynamic component, so in C and D respectively. So over the mid-latitude regions, the response is mostly governed by the dynamic change. It causes an equatorial shift of the AR over the North Atlantic, and it's northeastward extension of the AR over the North Pacific. And this is consistent with the wind response, so in E. So you can see that over the North Atlantic, the westerly jet shift equator were in response to RTCI loss, but it stands northeastward over the North Pacific. But if we look at the thermodynamic response, the change mostly confines over high latitude regions around pole of 60 degrees north, and it causes an increase nearly everywhere, especially over the barren characteristic regions, and this is also consistent with the response in the moisture field. So although we found significant signals in the mean response, we also noticed that the signal to noise ratio, we also found that the mean response, the magnitude of the mean response is relatively small, so compared to the noise. So the noise in here is defined as the standard deviation of the winter AR frequency across all 900 members. So for example, if you can see that, or even over the North Atlantic and the North Pacific Ocean basins, the magnitude of the mean response is only ranged from about 10 to 20% of the noise, and it reaches up to about maximum of about 40% over the barren characteristic regions. And this small signal to noise ratio in the mean response is largely caused by the intermodal spread in the AR response. And this figure is showing the AR response in individual models, and it's quite obvious that there's a large intermodal spread in not only the spatial patterns, but also in the magnitude. And we can quantify this intermodal spread by simply calculating the standard deviations of the response across models. And as shown in A here, and you can see that the largest model spread, intermodal spread, occurs over the ocean basins, over the North Pacific and North Atlantic. And we then decompose this total uncertainty into dynamic components by calculating the standard deviation of the dynamic response across model, and a thermodynamic component by calculating the standard deviation of the thermodynamic response across model. And it's immediately obvious that the intermodal spread is mostly caused by the spread in the dynamic response, while the thermodynamic response is quite robust across models. Indeed, if we look at the zonal wind response in the visual model, we can see that there's also a large intermodal spread in this response. Like for example, the ESM5, ESM2, this model has a very strong weakening of the westerly jet at around 60 degrees north. But however, if you look at other models, the weakening at around 60 degrees north is substantially smaller. But if we look at the moisture field, the response in individual models is a lot more robust across models. So so far we have been looking at this response uncertainty by decomposing into a dynamic and thermodynamic components. But the response uncertainty can also caused by either internal variability or model difference. So to identify the leading modes of uncertainty associated with the internal variabilities, we apply a EOF analysis to the winter AR frequency response across individual members, so 900 members in this case. And the first two leading modes of uncertainty over the North Pacific is shown in panel A and panel B. So the shaded contour is the anomaly associated with these leading modes, and the solid contour are the climatologies. So the first leading mode over the North Pacific is basically representing the response uncertainty on the strengthening of the AR frequency over the AR coalitions. And its associated wind pattern also showing a strengthening of the westerly jets. And the second mode basically describe the response uncertainties on the northeastward extension of the AR. And also the associated wind pattern also showing a northeastward extension of the westerly jets. And the first two leading modes of uncertainty over the North Atlantic is shown in panel E and panel F. And the first mode is representing the uncertainty on the meridional shift of the AR, and it's also its associated wind pattern is also in the meridional shift of the westerly jet. And the second mode is basically representing the eastward extension of the AR, and consistently the associated wind pattern is also showing an eastward extension of the westerly jet. And besides internal variabilities, model difference can also influence the uncertainty in the response. So to identify the leading modes of uncertainty associated with model difference, in this case, we apply the EOF analysis to the ensemble mean AR response across individual models. So we only have 9 models in this case. So basically, the leading mode of uncertainty associated with model difference are very similar to those associated with internal variabilities, except that they are noisier in here. And this is mostly due to a much smaller sample size. In this case, a 9 model only have here. And we further found that this leading uncertainty mode identified here can be used to describe the AR response to RTCI loss. So for example, over the North Pacific, the AR response projects very strongly onto its second uncertainty mode, which basically represent the uncertainty on the northeastward extension of the AR. But over the North Atlantic, the AR response projects strongly onto its first uncertainty mode, which basically represent the uncertainty on the meridional shift of the AR. And it's also worth mentioning that in another separate study, we found that the uncertainty mode identified here can be also identified in both lead analysis and A-mid model from the CIMIC test as the leading modes of winter AR in the annual variability. So and we also further found that this mode or this uncertainty mode in this shown in here can be occur naturally due to internal variability or driven or forced by seasonal temperature variability. And in here, we again saw that for the second mode over the North Pacific and the first mode over the North Atlantic, they can also excited by RTCI loss. And previous study have found that in response to anthropogenic warming, the westerly jet is going to shift towards. but the polar shift of the vestry jet depends on how well the model simulating the climatological jet positions. Basically, a model with a more equatorial located climatological vestry jet tend to exhibit stronger polar shift under warming. So in this study, we want to know whether a similar relation exists between the AI response to RTCI loss and how well models simulating the AI climatologies. So what we found is that over the North Pacific, so in panel A and panel C, it seems that model with a more westward located climatological AI coalition tend to exhibit a stronger northeastward extension of the AI under RTCI loss, and its response also project more strongly onto its second uncertainty mode. And over the North Atlantic, so in panel B and panel D, a model with a more polar located AR climatological maximum regions tend to show a stronger equatorial shift under RTCI loss, and its response also project more strongly onto its first uncertainty mode. So the result here seems to suggest that potential emergent constraints between AR response to RTCI loss and how well the model simulated the AR climatologies potentially exist. But however, we also know that the relationship presented here only based on 9 models, and each model only have 100 members, while previous study have been suggest that 100 members in this PA-MIP experiments probably is not enough to suppress all the internal variability. So in order to verify the robustness of the result, the relationship present here, we definitely need more models, and each model we need more ensemble members. And so here's the summary. In this study, we found that in response to RTCI loss, the atmosphere extend northeastward over the North Pacific and shift equatorial over the North Atlantic. And the uncertainty in the AR response are mostly due to the uncertainty in the circulation or the dynamic response. And AR response to RTCI loss seems to exhibit some mean state dependencies, and suggesting that potential emergence constraints may insist to reduce AR response uncertainty to RTCI loss. And this work has been published in your physical research letters. If you are interested, you can learn more about our study by using these papers. And thank you for your attention.
Thanks very much, Weiming. I have a similar question to the one I asked Christine. You looked at several of the climate models. I would imagine that they have a range of spatial resolutions to them.
Right.
Did you note any change in the response of the models that might have been associated with the spatial resolution?
Yeah, we also have briefly looked into this, but we didn't find any dependency on the model resolutions. So basically, all models, regardless of their spatial resolution, you give you a very similar climatology. At least the AR frequency, we focus on the AR frequencies. That the spatial pattern are quite similar. The difference is quite minor, we would say, and there's no obvious dependency on the spatial resolutions. Yeah, but I do think that if we have more models and we can increase the spatial resolution to even finer spatial resolution, we may see some dependencies, because study have been also focused on this PA-MIP model. They have found that all these PA-MIP models tend to underestimate the eddy feedback in this model, tend to be too weak compared to observations. But if we increase the spatial resolution to even finer scale, probably we can enhance the eddy feedback. Then we may see some a spatial resolution dependency on the response.
Is that what we're seeing in these results then? So you focused here on the winter time. So right. In a warming climate, you still have cold conditions in the Arctic. So you've essentially enhanced the meridional temperature gradient. And so the atmospheric river patterns have become more zonal. Is that what's going on here?
Can you repeat your question again?
Is the response to atmospheric rivers that you've shown here, is that related to the meridional temperature gradient in a warming climate?
So I think, yeah, definitely. I think because when you have RTCI loss, you weaken the meridional temperature gradients, and I think to some extent that caused the shape of the battery jet. So I think if it have yeah, if you influence the AI response, yeah.
Okay. Do we have any other questions for Weiming?
There's one in the
there's,
chat.
yes.
And Mindy, sorry.
Mindy, yes. Mindy Bergman, would you like to unmute and ask your question?
Yeah, sorry, I'm battling with the computer here. Thanks, Weiming, really great talk. We're really interested in the Arctic as well. We're in Canada, the Environment Canada. I was just wondering, what do you think will happen with atmospheric rivers when we get an ice-free ocean in the Arctic all summer and in the fall and maybe partly the winter? And a question related to that is, when we have these storms in the Arctic, wouldn't they regenerate their own strengthened atmospheric rivers and affect the whole coastal areas in the Arctic more?
So so I think that if we have a CI-free Arctic, I think these atmospheric rivers are going to strengthen because you definitely right now, if you have a CI cover the Arctic, the moisture source mostly originate from lower latitude regions. But when you have a ice-free Arctic, now you have a lot of ocean exposed to the atmosphere. You can also, a lot of moisture can surprise locally from a local source. That would enhance the IVT, basically IVT integrated water vapor transport. That would enhance the AR strength. So, and probably causing the AR to be last longer, a little bit more persistent. Yeah, but I'm not sure how the dynamic will respond to the ice-free Arctic. I would suspect that if you have more moisture, more latent heat release when you have precipitations, so you may end up having also a stronger precipitations. Yeah.
Thanks, good work. I hope you keep it up. We need a lot more information. The Arctic is changing so fast.
Yeah, thank you.
Any more questions? Peter Weiming for Christine.
And I also see a question in the chat.
Yeah,
So,
Wisla Maslowski, would you like to unmute and ask your question?
Sure, yeah. Thank you very much for this talk. Really appreciate it. My question is that, could you comment on the importance of the atmosphere-ocean coupling in affecting the response of atmospheric rivers to ice reduction, and how this effect potentially might impact your findings?
yeah, so in our study, we use only atmosphere only model. So, and it seems that if you enable the atmosphere ocean couplings, the response is going to amplify based on previous study. And also, besides that, it also allow not just the signal we amplify, we also allow the signal to transport to a even lower latitude regions, and also even cross the hemispheres. So our result present here probably represent the lower bound of the response, because we only use atmosphere only models.
Thank you.
Any other questions for Weiming?
I have a quick question here.
Yeah.
Very nice talk, Mark. You mentioned earlier, you said you have used 9 model with 100 members. What do you mean members? It's the AR members or the ensemble members?
So in ensemble members, so each model will have for each model and each experiment, they have 100 members, and each member only run for 1 year. Run for one year. Yeah.
Okay, thanks. Because I didn't expect ensemble to have so much, like 100 ensemble.
Yeah, because each member only lasts for 1 year, so they can afford to.
Yeah. Sorry, maybe I can follow up on that. Nice talk with me. Mike and I had some chat about this experiment design. Mike think that the artificial ice setting could affect your results, but I know that you didn't run those simulations. You used those from PAMIP.
Right.
Do you think is there, if you could, like, you design your own experiment to do this kind of study, what kind of experiment design you would want to change in order to better study the role of sea ice in a historical period or even into the nearer future?
If I would decide this, I'm going here that the experiment that future CI loss is under 2-degree warming, right? And they also show that 100 member is not enough. If I were to decide, I probably would decide like under even stronger warming, so that I could have a stronger signal, right? Have a stronger signal, and also 100 member probably may increase the number of members, and also maybe CI occurs in different regions instead of just the CI concentration reduction from model, from simplified model, I believe. Maybe we can have CI reduction at different regions. Yeah.
Great. All right, thank you.
How long do you know why PAMIP elected to have that kind of configuration for their experiments?
PAMIP, I think the big many constraint, they want to have a big ensemble member, so they have to design the simulations pretty like big perturbation, like you.
I see.
That's my understanding.
Mike, did you want to add anything?
Well, maybe not on that subject, but on the related subject of air-sea coupling that Vislav asked about. I collaborated on a paper with Kent Moore and others a few years ago. We tried to explain why the Beaufort gyre reversed in the winter a few years ago. And the explanation seemed to be that the Icelandic low intruded into the Arctic, kind of, sort of ate the Beaufort high in winter. And Ken thought that it was the air-sea coupling, thin ice, heat coming up from the ocean through that thin ice and somehow paving the way for the Icelandic low to intrude farther. So I'm just wondering if that's a thing that might be enhancing atmospheric rivers. I don't know.
Well, I wanted to ask Christine about this again. We talked at the AMS meeting quite a bit about atmospheric rivers, but one of the initial parts of Reggie Newell's paper was that there was a tropical moisture source. And it seems that for Arctic atmospheric rivers, that might be too specific of a definition, that there's probably a lot of air-sea interaction along the way of an atmospheric river, and that there's probably a lot of moisture sourcing local as well as remote. Would you agree with that?
Yeah, I mean, this is sort of the $1 million question, like what in terms of, how are we defining atmospheric rivers? I think when those first few papers that came out on atmospheric rivers were very, focused, I think, sort of on mid-latitudes. But since then, there's been like an explosion of literature and interest in atmospheric rivers. So that's why I sort of modify the definition to say it's sort of like transporting moisture across climate zones, so subtropics into mid-latitudes into Arctic. It's just really this transport of moisture. And then you can sort of, in terms of where the moisture is sourced from that is falling out of the AR can also, I think, is also a little bit different depending on what region you're in. For example, Pineapple Express version of atmospheric rivers. These are the ones that come from like the subtropics in the Pacific, the Hawaiian region, why it's called Pineapple Express. Those often, if you do there's been a number of water tracing studies that show that a lot of those atmospheric rivers are actually the moisture sources that indeed the subtropics. However, if you look at Atlantic Ocean atmospheric rivers impacting, say, European regions, you see a lot of these are actually that the moisture that the precipitation, the water that's coming out of those is actually internally sourced basically from the uplift of the warm conveyor belt, and not, but you have that, you know, the moisture stream, the integrated water vapor is, you know, subtropic, you know, originally, but by the time, you know, you have all the air sea interaction and back and forth, by the time you actually have the precipitation that's coming out, you know, of the atmospheric river over, you know, Iberian Peninsula or something, you know, that may be more of a warm conveyor belt sort of a feature. So there's different flavor, I call them different flavors of atmospheric rivers. And it also goes to like what you call, how you want to define it, you know. So is it simply moisture transport, or is it always have to be connected to an extratropical cyclone? And there's disagreement in the community between those two things.
All right, Hazel is reminding me that we're getting towards the top of the hour here. So I think I will commandeer the host preference here so we can go for a few more minutes here. But I see that Ola has his hand raised. Ola, would you like to ask a question?
Yeah, I was kind of a question comment. It touches on the subjects here of the Beaufort High that Mike raised, as well as the penetration of these, I'll call them moisture intrusions, because into the Arctic, that seems to be the bigger impact is on the moisture rather than on precipitation. But I was involved both in Sheba and Mosaic, and we had a study on a Sheba case where a moisture intrusion came through the Fram Strait, so from the Greenland Sea region, penetrated across the North Pole, all the way to the Sheba site in the Beaufort Sea. And this is in January. And so a midwinter case. And it impacted dramatically the temperature near the surface. The moisture was aloft at about 1,000 to 1,200 meters above the surface. And so it was a long wave radiative effect, and it produced a thermal wave that penetrated down through the ice, through snow, through the ice, to the bottom of the ice, and slowed the ice growth, which occurs at the bottom of the sea ice. So these thermodynamic effects of these moisture intrusions can be very significant. And we have a number of cases that we're looking at also now for Mosaic. And there's going to be some similar types of events. We see these thermal waves penetrating through the sea ice as a response to these moisture intrusions coming in, again, near the North Pole. So that there's a number of those events. So there'll be more results coming out on these kinds of studies. But these are, I think, categorized under these atmospheric river events, but I would almost call them atmospheric creeks. Because the amount of moisture vapor transport is not nearly as large as the original definitions that Marty Ralph came up with and the Newell paper talked about. So, but these atmospheric creeks for the Arctic are really very important in the radiative sense.
Hey, Ola, that's a great paper. But remind me, would you say that by the end of that winter, in the Sheba case, you know, ice thickness was less than it sort of should have been?
Well, we haven't done that calculation, but obviously the thickness or the ice growth slowed, so one can presume it did. Now the question is, does the whole ice pack respond then to growing faster after the effects of that warm air intrusion or the warming event passes? We have a case from Mosaic in the springtime when we show that the ice growth slows in April, but then we're looking at the onset of the summer melt, And we thought maybe that event speeded it up, but it didn't. There's a paper being written on that. Chris Cox is leading that one. But that was because the thermal structure within the sea ice, it changed. Well, we did some modeling where we tried to say, all right, if this event didn't happen, what would have happened? Which is the question you're asking. and after about a week, the system catches up.
Okay.
But anyways, stay tuned for that paper. so yeah. So that was more the comment, whether this event impacted the Beaufort gyre, I don't know, but it did penetrate all the way from the Atlantic side across the North Pole. So that definitely were some effects there.
I think certainly from a modeling aspect, the rate of effects of these atmospheric rivers and the energy effects are certainly of interest. Certainly, I come at these from looking at polar ice sheets, and I think there's a lot of interest in understanding whether these how these events affect surface melt on the ice sheets and things like that through the rate of effects. Ruping, you still have your hand up. Do you have another question?
Yeah, I just want to add a quick comment to Christian's opinion about the source of the atmospheric river. The moisture source may not be that important. I think most important thing is the transport component, the dynamic or thermodynamic associated with the transport. Like especially in winter times, in summertime, we can see the atmosphere is quite moist in a lot of places. But if you don't have wind transport to organize that moisture flow, that may not have that important impact, especially like transport, not only just moisture, also transport energy as well. Yeah.
Agreed, totally.
Yeah, and that energy transport that you're saying, if those clouds that are associated with that moisture transport are warmer because of the thermal transport also, their long wave effect is going to be larger.
Yeah, that's true. But also like sensible heat transports, yeah, that's where the latent heat, maybe the component of latent heat actually is smaller than the sensible heat transport.
Well, if you're going to get the sensible heat down to the surface, you have a problem over the sea ice, for instance, because you have this basically constant inversion, and which is actually strengthened with this warm air coming in the loft. And so you have a very stable layer there. So getting the turbulent mixing to mix that warm air down to the surface is not very effective. The long wave radiation is really the most effective mechanism to bring that heat down. And so we've seen that basically the long wave radiative effect tries to get a radiative balance between the air that's in that cloud of air aloft and the surface. It doesn't always succeed, but that's what it's trying to do. And so if the air aloft is warmer, it's trying to warm up the surface to that temperature of that air aloft. The sensible heat flux, the turbulent sensible heat flux is, I think, secondary because of the very stable layer that you have there.
Yeah, yeah.
And Mindy, you have your hand raised.
Yeah, thanks. This is a question related to that, and Ola and maybe women can say, when we get atmospheric rivers in the Arctic, they're going to give some snow on the surface. And so they're going to affect the whole coupling with the stability. I'm not a sea ice expert, but I would expect it would insulate it from the cold and cause the sea ice to more rapidly break up? I don't know. Just wondering if you might comment on the effect of atmospheric rivers bringing snow and then the feedback there. Thanks.
Yeah, I unfortunately I didn't know too much about how atmosphere brings snow to the artist. I focused on how AR can affect RTCI loss. It basically can induce RTCI loss, but I'm not sure how the effects of the snow bring by the AR will affect its CI stability. Yeah.
That's a very good question now. And that's something that you can do with models. You can test, you can design experiments to try to test that.
I'll just add to that even stronger points to the need for coupled model simulations.
Yeah.
Yeah, that's great. Well, thank you, everyone. It was really good discussion. And
Yeah.
We've seen cases where that in the fall, when one of these moisture intrusions produces snowfall, that's the kicker to raising the surface albedo and to really start the freeze up process. So Mindy, your point is well taken that the snowfall can be really important, especially at certain times of the year.
All right. It's now gotten to 10 minutes after the hour. I think we can close here. I'd very much like to thank our two presenters, Christine and Weiming, for their presentations. And I'd like to thank everyone for their comments and the discussion. The modeling collaboration team will have another topic for next month that we're still working on, but otherwise, I think we're going to close right now. Thanks very much again, everyone.
Thanks, Richard.
Thanks.
Thank you.
thank you. Great talk.
Thank you. Bye-bye.
Thank you.
All right. Bye-bye.